Asteroid 2024 YR4 will not impact the moon in 2032. New ways to measure the expansion rate of the universe. Jupiter is smaller and flatter than we thought. And in Space Bites Plus, even tardigrades struggle in Martian Regolith. All this and more in this week's Space Bites. I have some terrible news for you. And that is, in 2032, we are not going to watch an asteroid slam into the moon. That sucks. The asteroid, this is 2024 YR4, which was discovered last year. And when it was first found, it is coming close enough to the Earth-Moon system that astronomers were a little bit worried that it might have a chance of hitting the Earth. And of course, then whenever that happens, they direct the world's Earth and space telescopes to take more observations of its orbit. And by doing so, they confirmed that no, it is not going to hit the Earth in 2032. But then there was still a chance, a 4% chance, that it might slam into the moon during that period. And so, I mean, that's exciting. And so to find out whether or not this was actually going to happen, astronomers directed the James Webb Space Telescope to make the most accurate measurements that you can of this asteroid night after night as it's moving through the solar system. And they found that it's not. That it's going to come within 20,000 kilometers of the moon, but it's not going to hit. It would have been cool to be able to go outside and watch the moon at exactly the right time and watch a flash on the surface of the moon. And then maybe we would get just a great meteor shower a couple of months later, but nope. It's just going to be a very close flyby. I'm sure you're familiar with the idea of the habitable zone. This is the place within a star system where planets can have liquid water on their surface. And it doesn't mean that the planet is inhabited, but it's pretty hard to have life on the surface of a world without liquid water. Life as we know it, anyway. But when you take this idea of a habitable world and then think about what a habitable sort of exploration empire might look like, then the idea of a habitable zone kind of changes. A previous guest of mine, Caleb Scharf, recently put out a paper where he investigated what would be the habitable interplanetary zone. So he was thinking about, what if you had an advanced civilization and they were looking to expand from star to star, to go from place to place, and that some stars, like the sun, are going to be very habitable. You're going to have good temperatures, not a problem with radiation, lots of resources available in the solar system. This is a good place to set up shop. But there are other systems where the radiation is bad, there's not a lot of resources, they're going to be bad. And if you tried to stick around too long in that system, you might suffer damage, you might die, you might starve. And so then if you think about how you would be expanding, leapfrogging from world to world, what paths would you take and how quickly would you expand? And so he identified 4 criteria for this. 2 of them are good, which is that you have power availability. You essentially have lots of radiation coming from the star that you can use to fill your solar collectors, to power your interplanetary laser systems, and so on. And then you have the material resources. Is there an asteroid belt with lots of metal that you can send your von Neumann probes into to replicate themselves? And then you have 2 that are net negatives. So you have the radiation environment. Now think about a place like the TRAPPIST-1 system where you've got these flares that are causing devastating radiation damage to anyone that tries to stay within the system. In fact, he calculated that you'd only really be able to live in there for about 45 days without some kind of extreme radiation protection. And then the last factor is the difficulty of transport. Can you get the delta V to move on to the next star system? And so then when you put all that together, you can sort of chart the kinds of paths that advanced civilizations might need to take as they're moving from star system to star system. Some of them, like the solar system, are ideal. We've got all of those bits and pieces in nicely balanced, but others like the TRAPPIST-1 system, too much radiation, not enough energy available to power your flight, maybe not enough resources. And so you can figure out what a sort of more realistic expansion of an advanced civilization might look like. We got a story about this from Andy Thomaswick on Universe Today. Jupiter is the largest and most massive planet in the solar system. It accounts for almost all of the mass in the solar system that isn't the sun. But it turns out that Jupiter is a little bit smaller and a little bit flatter than we previously thought. So how do you measure the size of a planet, and especially a gas giant planet? Well, when the spacecraft visited Jupiter in the past, the Pioneers, the Voyagers, right now we have Juno, they are communicating back home with their radio instruments. And so they have the signal that's going back and forth between the spacecraft and Earth, and Jupiter passes in front of the radio signal, cutting it off. And astronomers have used this to measure the exact size of Jupiter, calculating at those points when it cut off the communications. And what they found is that the new polar radius of Jupiter is 66,842 kilometers, which is 12 kilometers less than was previously estimated. And the equatorial radius is 71,488 kilometers, which is about 4 kilometers less than the previous measurement. So both the polar radius and the equatorial radius are smaller, but the polar radius got smaller more than the equatorial radius did, which means that it is smaller and is also flatter. And so when you compare the flatness of Jupiter to the flatness of Earth, it's about 20 times flatter. And so, obviously, if people believe that the Earth is flat, well, Jupiter is 20 times as flat. We've got a story about this from Lawrence Tugnetti. Astronomers have completed the most detailed radio measurement of the entire universe at very low frequencies. This was done using the European LOFAR network of radio telescopes. And just to sort of give you a sense of the scale of this, in this new cosmic map of the universe, there are 13.7 million individual objects that are radiating radio waves. We've got all kinds of stuff. Interesting stars, pulsars, but supermassive black holes that are accreting material. There's a lot of really interesting objects out there. The LOFAR array is actually 52 radio telescopes that are working together across Europe. 38 of them are in the Netherlands, and then the rest are sort of spread out across Europe. Together, these radio instruments have gathered 18.6 petabytes of data. They've been scanning the sky for 13,000 hours. And then all of these data have been crunched down into this map of the cosmos in this low frequency radio wave data. If you're a radio astronomer, this is really interesting. Lots of targets to look at and then align with other wavelengths. Look at how they look in visible, look how they look in X-rays and so on. But where this is interesting to me, and maybe to you, is for the SETI researchers, people who are looking for signals from extraterrestrial civilizations, because, the universe is really big. And there's lots of places to look. You don't really know where to look at which frequencies and so on. And so now you've got this just survey of the entire universe in this frequency range that maybe they can find individual signals hidden within that. So, if there are signals in there, it'll be the SETI researchers who might find them. We've got a story about this from Matt Williams. And now we've got a couple of ways to measure the expansion rate of the universe. And, this is something that we've been talking quite a lot about here on the channel, the crisis in cosmology, the Hubble tension. And this is where when you measure the expansion rate, the Hubble constant of the universe nearby using Cepheid variables, type 1a supernova, you get one number. And then when you measure it in the cosmic microwave background radiation, you get a different number. And the two numbers have error bars. The error bars don't overlap. This is a mystery. And so astronomers are always on the hunt for new ways to measure distance in the universe. With that, they can then measure the expansion rate of the universe. And so we've got two new interesting ideas that astronomers are working on. Unfortunately, neither of them have given us the number, but they are sort of on their way to give us the number. So the first one is a measurement of a really interesting gravitational lens where astronomers measured a foreground galaxy cluster. And then behind that is a galaxy that had a supernova go off in it. And then the light traveled around the cluster and took 5 separate routes before we were able to see it in the telescopes. And so because the light is following a different journey around the gravity of this galaxy cluster, it has a different time that it appears. And so from that, astronomers are able to measure the expansion rate of the universe just by the different paths that the light had to take to get around the galaxy cluster. We've seen this before, but normally you get to see, say, 2 examples of the supernova or 4 examples of the supernova. And so this is 5. So this gives more accuracy. And, what did they find? Well, we don't know yet. We're still in the process of them measuring the length of time that the supernova shows up in each one of these separate images. And then once they've sort of seen it all the way through to the end, calculated everything, crunched the data, we should get their independent measurement of the expansion rate of the universe. And so that's one trick. And then there's another one, and this is using gravitational waves. Essentially, all of the ways of measuring the expansion rate of the universe, the Hubble constant, this is done using the electromagnetic spectrum. When you're looking at Cepheid variables, you're measuring the light coming through them. When you look at type 1a supernova, you're measuring the light. When you look at the cosmic microwave background radiation, you're still looking at light. It's just microwaves. But gravitational waves have given us this completely independent way to measure the universe. You are probably familiar with LIGO, where we are detecting gravitational waves from colliding black holes. Now, in addition to the specific hundreds of collision events that LIGO, Virgo, Kagra have detected, there is this larger just gravitational wave background that is coming from just the mergers that are happening in all directions at all times that you're not able to pick out those specific events. And right now, we're not able to detect those specific events, but it's believed that in the next couple of years, with more upgrades to the LIGO, Virgo, and Kagra instruments, we might get to this place where we are able to detect more of those background gravitational wave events. But because they haven't been able to detect them today, that still allows astronomers to set constraints at how many and how much of these background gravitational wave events are happening. And so when you combine the gravitational waves from actual colliding black holes, as well as the measurements of this background gravitational wave collisions, then you should be able to get an estimate for the Hubble constant that is, like I said, completely independent from the ones done with the electromagnetic spectrum. And this is sort of going to be an entirely new age, because these cosmic sirens allow you to measure the distance sort of precisely, exactly. The frequency of the chirp gives you the energy released, and that allows you to know the distance to the thing. Part of the problem with measuring with the electromagnetic spectrum is that it's really hard to know the inherent brightness of an event. Think about, say, the brightness of quasars. If you could figure out intrinsically how bright quasars are, then that could tell you their distance, and they're very bright, very far away. But the problem is there's just too much variability about the brightness of a quasar. But with these gravitational wave events, you can measure their distance purely from the collision, the characteristics of the collision. The problem right now is that that measurement isn't very precise. You have these big, wide error bars, and that it means that you don't have a method that is better than measuring other things like, say, type 1a supernova. But over time, as we get better versions of the LIGO, Virgo, and Kagra, then you're going to get those error bars come down to the point that you actually have the best distance measurements are coming from gravitational wave events. The astronomers estimate that within about 6 years or so, we'll get to this place where we will be detecting these background gravitational wave events in addition to the direct events, and that will give us another independent way of measuring the Hubble constant. Now, we've got stories about both of those from Matt Williams. Last week, we reported that NASA is switching up the way the Artemis missions are going to go. Before, we had Artemis 2 is going to go around the moon, Artemis 3 was going to bring humans to the surface of the moon, and then Artemis 4 and ongoing, maybe they build the lunar gateway or start building a base on the moon, who knows. But now Artemis 3 is going to test out docking in Earth orbit. So you're going to launch with a space launch system, an Orion capsule is going to dock with either Starship or the lander from Blue Origin and just demonstrate that that technology is going to work. And then Artemis 4 would bring astronauts to the surface of the moon. And this week we got new legislation from the Senate that gives NASA a bunch more instructions. So the first issue is space station in low Earth orbit. Now, as you probably know, the International Space Station is due for deorbiting in 2030. That SpaceX is supposed to create a tug that is going to help deorbit the space station by then. And we got an announcement that the Senate wants to extend the life of the station into 2032. So that's 2 extra years. The second thing is that they have directed NASA to find commercial partners for space stations. So there's a couple of examples. There's VAST that we've reported on before. There's Axiom Space, and there's a bunch of other companies that are hoping to do commercial space stations. And so just within the next probably couple of months, NASA is going to start to enter into negotiations with some of these companies, set out contracts, and start to move towards this time when, after the International Space Station is deorbited, that then NASA still has a presence on various private space stations, so they continue to do research. And then as part of this, it looks like they really want to push towards having a base on the moon. Less emphasis on some kind of space station in lunar orbit, say with the Lunar Gateway, and really push towards having a permanent human presence on the moon. So this is all kind of unfolding right now quite rapidly. I feel like I'm getting whiplash from all of the cutbacks that we saw to now all of this enthusiasm for it. And hopefully we will get a much better sense of this in the next few months. Every week we do a vote on our channel where you tell us what you thought was the best space news story of the week. And the winner last week was that Vera Rubin is now live. What a surprise. So thank you everybody who voted last week. Once again, we're going to put this week's vote into the post tab here on our YouTube channel. If you want a better chance to see the polls, click on subscribe, click on the notifications bell, like this video, and that will encourage the algorithm to show you more stuff like this. We talk a lot about Dyson spheres here on this channel. This is the idea that eventually advanced civilizations will just keep building more and more satellites around their star. Eventually, they will be utilizing all of the light that would have gone off into space. They're going to be capturing it and using it for some purpose. Normally, we have this very solar system centric version of what this Dyson sphere would look like. Let's build a Dyson sphere that is the distance from the Earth to the sun. But that's probably not the ideal way to build one of these Dyson spheres. There are better star systems for this kind of thing. For example, a red dwarf star, and not the active red dwarf star like the TRAPPIST-1 system, but one that's had a couple of billion years to settle down. You could build a Dyson swarm around that smaller red dwarf star with a fraction of the materials and be able to harvest all that energy coming off the star. Or think about a white dwarf, that white dwarfs do give off energy, and they're very stable for very long periods of time, billions of years. And you could set up your Dyson swarm only a mere 1,000,000 kilometers away from the white dwarf and surround it with the leftover debris from that star system when it used to be in its prime. And so astronomers have thought about what would it look like to find a Dyson sphere around one of those stars. The star might have a surface temperature of like 3,000 Kelvin. It's going to be red, but your Dyson sphere is going to be blocking that light, and it's going to bring that temperature down to about 50 Kelvin. That's something that's visible in the infrared. In fact, that's something that is perfect for James Webb to be able to resolve. So astronomers have proposed, doing a wide field survey of the cosmos, look for these sources that are kind of point-like at this temperature that could be Dyson spheres around red dwarfs or white dwarf stars. We've got a story about this from Andy Thomaswick. If you've watched The Martian, then you probably know that Mark Watney has to grow potatoes in human manure to be able to survive. Growing plants requires bacteria in the soil, and Martian Regolith has none of it. Well, it also has toxic perchlorates. You need to wash that out. But once you've done that, then you would need some additional nutrients to be able to help the plants grow. And in The Martian, this was solved by going out to the outhouse and bringing in all of the astronaut poop to be able to grow the potatoes. And scientists wanted to know if this is realistic. And so they took simulated Martian regolith. Essentially, you can buy simulated material that has the same kind of chemical composition as Mars regolith. And then they mixed in human effluent, which is as nasty as it sounds, and let that sit for about 24 hours. And what they found was that the effluent actually started to break down the regolith and release more of the nutrients that would be required for plants. And it moved the regolith towards a better medium for growing plants into. And so, yeah, when we go to Mars, if anyone does set up a city on Mars, that they're going to be growing plants in their poop. There's just no way to get around it. We've got a story about this from Carolyn Collins Peterson. All right, time for some cool pictures. The Cat's Eye Nebula. This was taken by the Euclid mission and the Hubble Space Telescope. And this is a beautiful example of a planetary nebula where you've got a star that is dying. In this case, it's a Wolf-Rayet star, and it is blowing off its outer layers into space. And when you look at the Cat's Eye Nebula from the Hubble Space Telescope, you're looking at the center part, which is this crazy twisted up nebula. It's actually thought that there might be a binary star system in there where the two stars are whirling each other up, that jets are being twisted around, and that's why you have this very strange shape. But Euclid gives you this much wider field of view, and so you can see this larger set of shells around the Cat's Eye Nebula. These are the past shells of its outer material that the star blasted off into space around it. It's a great picture. It's one of my favorite nebulae, and this is a great story from Evan Goff. I hope you're enjoying this week's episode of Space Bites. We've got a lot of stories here, but we feel that there is a better place to watch our content, a place with no ads, a place where you can just subscribe to our content and receive notifications when they happen. Doesn't that sound amazing? Well, that place is Patreon. And to encourage you to go over and watch our content over on Patreon instead of here on YouTube. And remember, this is all completely free. There's no ads. You don't have to donate. You can just watch it for free. Click right now. It'll just open up. You can watch it. But to encourage you, we have put one more story into this week's episode of Space Bites. And the bonus story this week is about how tardigrades suffer when they go to Mars. So remember, there's a link in the show notes. You can check that out. And this is just a fraction of all of the space news stories that we're covering over on Universe Today. And if you want just one digestible version of everything that we're covering, I write a weekly email newsletter that I send out to 70,000 of my closest friends. It's completely free. There's no ads. I write every single word in this newsletter myself. You can go to universetoday.com/newsletter to sign up. All right, I'm going to talk about a couple of episodes that we're about to release that are going to be very special, and I think you're going to want to keep an eye out for them. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear Lake Roofing, Brian Bodie, Carradwin, Chuck Hawkins, Commander Bailock, Cooper and Ellie, Dark Finger, David Giltonen, David Matz, Evan.pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Smith, Michael Purcell, Nordspace, OneStepForAnimals.org, Porobuk, Rankaidu, Richard Williams, Sean Sargent, Stephen Filemunley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means universe to us. So we're working on a couple of episodes right now that I think you're really going to enjoy. One is that I just wrapped up another interview with Lee Feinberg. He was one of the designers for the James Webb Space Telescope, worked on the Hubble Space Telescope, and he was the principal architect for the Habitable Worlds Observatory. He is also now the mission architect for the Large Interferometer for Exoplanets. So these are the two spacecraft designed to find Earth-sized worlds orbiting around sun-like stars. He's a legendary spacecraft designer, telescope designer, architect, and is just so generous with his time. And so we have what I think you're going to find is one of the most interesting conversations about telescope design, what's coming with all of these next generation observatories. So I just want to warn you that that episode is going to drop on Monday. And so if the algorithm fails to show it to you, it has happened, and it's going to be one of the best interviews of the year. I think you're really going to love it. And then we've also got another 4 interviews in the pipeline right now that are in editing. So we're going to probably release at least 2 interviews a week for the next few weeks. And then the second thing is probably going to drop over the weekend, maybe tomorrow, and it's going to be something big. And I'm not going to give you any more information, but let's just say it is going to be gigantic. It's going to be huge. All right, we'll see you next week.